Okay. Hello, everyone. I'm going to be telling you about choosing data model comparison metrics. Um, Oops, I need to click on the right thing here. A few years ago, the CCMC had this conference on assessing metrics and space weather capabilities down in Florida. They had another one last year, right before COVID locked everyone down. But the first one, I was in charge of one of the working groups for that, and we developed a paper from that that ended up with this as one of the several tables in it. This one is for KP. And different people that have tried to predict KP and the different styles of how they did their prediction. And this last column over here is showing the metrics that they used, the data model comparisons that they used. And a lot of people use root mean square error and R, the Pearson correlation coefficient. And a few people use some other things like, hey, MAE instead of RMSE, that's great. Heidke skill score thrown in there. Some people, prediction efficiency. Sometimes we'll throw in a mean error, but kind of a smattering of many different types of metrics. And you can make an ugly graphic from all of these different metrics that will just scare people away. And so you look at this, and people just seem to sort of throw a sticker at it and pick one of these and say that's the one I'm going to use today and move on. So I've taken it on to try and help to provide some organization to this. And so a nice, breathe a sigh of relief to myself of, when I think about metrics and go from this page and like, what am I supposed to do, down to something like this page, and I can feel more calm and less neurotic about it. What is this? This is organizing all these different metrics according to how they assess the different features of the data model comparison criteria. So RMSE, for instance, we were talking about that just a minute ago. It really is a accuracy assessment of the overall similarity of the two values, but it really doesn't actually tell you about similarity of centroids or spreads specifically. There are different things that you can't learn from RMSE. I'll get to that in a slide or two. For instance, and another one, the correlation coefficient isn't a measure of what I call association, similarity of the trends, but it actually does very little about whether the two values are close to each other. They could be far off as long as they're going up and down together. So many different metrics, and in fact, two different methodologies for even calculating these. I've just been mentioning what I call fit performance, that are ones that like to compare the exact values of the data, but there's also this whole other set of metrics, categorical designations for the values as either in event state or out of event state. And you can do that for both the data and model, and you create your 2x2 4 quadrant contingency table. And then there's many different metrics that fit into this methodology approach to assessing whether one model is good next to another. So what I would like to say today really is that metrics work well together, and that we shouldn't just be choosing one or randomly choosing a couple, but really there are different ways that these things go together, and we really should be doing this a lot more in terms of pulling in multiple metrics so that we can really get something useful out of extra than what we have been doing in terms of getting a useful a bit of information out of that comparison between an observational number set and a numerical number set. So, and really this gets down to, because each metric is designed to assess only one specific aspect of that data model relationship. So what do I mean by that? For instance, accuracy. I was just mentioning accuracy. These top two panels have exactly the same accuracy measure in terms of MSE or RMSE, but they're very different. one of them has really good bias, but poor precision. Nice big spread around here. This one, really tight precision, but poor bias. The whole thing is offset from the one-to-one unity line. This one down here might have slightly worse, but it's bad in both of the directions. This one finally has both of them good. So if you have a really good accuracy measure, okay, everything else, all the other measurements will also be good, but usually you don't have something that's that good. Usually there's some issue there, and so using these other metrics from the other categories allows you to really get into why accuracy wasn't as good as it was. And so this is one thing that I'm advocating here is when you pick an accuracy measure, also pick a bias and a precision metric so that you can really understand why accuracy is doing what it's doing. Another good pairing, one that a lot of people do use, is association with accuracy. So this is using RMSE and R together, or any two metrics out of those two different categories. Because what does association do? It really gets at whether there is a linear trend between these two. And so this one right here actually has really good association. But its accuracy isn't very good, and its accuracy is not good because the precision is not good. There is a small spread in the observational window, but a large spread in the modeling value window. Over here, you have good precision, but now you have poor bias. The whole thing is shifted away from the line. Still good association, though. All the values are falling pretty closely along a straight line. It's not until you get to this one where both of them are good. So you can have that. Whoops, sorry. Don't know what happened there. Extra information when you combine two different metrics from different categories together like this. And a third thing is subsetting that I really liked right here. And this, we like to use our accuracy in one way, to do an overall assessment, but you can actually do accuracy measurements on little chunks of the data model set. Here you're in discrimination and reliability are two such subsetting methodologies, and discrimination subsets along the observational values. And you can see that in this particular data set, it's really good in this third quadrant and not so good in some of the others along the observational values. This other set over here, you can see it's really good in one set and not so good in these others. So you can tell, oh, okay, this is the region that's giving me that poor accuracy value and not this region. The model is actually good down here in this set of model ranges. Over here, the model is actually good in this set of observational values. That's something that subsetting can really allow you to dig deep into why your data set is doing what it's doing. And of course, you can use these two together, exactly the same data set in these two different plots. When you divide it up according to observational ranges in discrimination, you see that the middle section is good. When you divide it up into reliability subsetting along the model ranges, you see that it's the lower set that's good. Exactly the same purple dots of these two different things. So what does this say? It says that the model is good at low model values, but the model is also good at mid-range observational values. Exactly the same model. And that's something that you wouldn't have gotten if you just did a single calculation with a single accuracy metric. A final thing that I'd like to say is sliding in terms of event detection. I haven't mentioned those much at all yet. So in event detection, one of the big powerful tools that you have there is sliding the model event identification threshold. And so this is how we produce the ROC curve, for instance. You have a given threshold for your observations in event state and out, and then you slide the blue curve in order to create your array of values for probability of detection and probability of false detection, and you can make your ROC curve from that. Another way to do that is with sliding both of them simultaneously. This is something I call a stone curve, and it produces a similar set of probability of detection, probability of false detection, as a function of threshold setting. But now you have these dots moving from hits not only to misses, but also to false alarms as the red curve goes up, and eventually ending up everything in correct negatives. So you can actually get non-monotonicities in the curve instead of just a monotonic curve. And a quick example of that, showing it here for a ROC curve, that's the blue curve, and then a stone curve that has this jump like this. What is happening here? This is because there was clustering. And a jump like that means that the model was actually under-predicting, systematically under-predicting the values in this particular range right here, which was in the, say, 30 to 50 nanotesla range of the DST index here at Earth. That's what this particular model assessment was about. And so you can see that the model was doing something different, and the sweeping of the thresholds allows you that extra level of robustness in your data model comparison. So I leave you with the chart again, saying that this is a way to organize all these different metrics, because there's a vast array of different metrics that you can choose. And I encourage you to be more systematic in choosing your metrics so that you provide yourself a more comprehensive analysis of what the model is really saying about the data and how well it fits. And I guess a final slide, I'll just say thanks to those that have helped with this, including Abby. Thank you, Abby.